So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Hajime Yano, who's come across to us from the Japanese Space Exploration Agency, JAXA. Hajime did a bachelor's in science and physics at the International Christian University in Tokyo, and then a PhD in space sciences at the University of Kent in Canterbury in the UK. His topic was micrometeorite flux in low Earth objects, in low Earth orbit. And then he did a postdoc at ISAS in Kanagawa in Japan, and then a second postdoc in the United States at NASA Johnson, where he was working on the Stardust mission. And after that postdoc, he returned to Japan and is now working at ISS as part of the JAXA effort. His career research interests focus around things such as the Hayabusa mission to asteroid Itokawa and the upcoming Hayabusa 2 mission. He was also involved in the Leonid's MAC mission that was with Peter Yenniskens here at the SETI Institute. He's interested in hypervelocity impacts and space debris and Antarctic meteorites, and also in upcoming missions and projects revolving around solar sails, which I'm sure we're going to hear a little bit about in tonight's talk. So please join me in welcoming Hajime.
Thank you, Adrian. Good evening. Okay, I need to can I have a laser pointer?
Maybe you could use the mouse.
Ah, okay, well, it was there when I first saw it. Oh, that's okay. All right, today it's my pleasure to come here in Mountain View. I think this is my first time in this institute. Every time I came here, it's always Ames, but it's nice to be in a different place. However, there's a number of the scientists belong to this institute. Is my coworker, Peter, was one of them. So in next 15 minutes or so, I would like to share this lengthy title. It says Scientific Premises and Technological Challenges, or maybe also Managemental Challenge as well, of the deep space round-trip exploration. I'll explain what that means later. And all the way up to Jupiter Trojans and even farther away. My talk will consist of like a mixture of past, present, and future. So the Trojan is a future bit, but in order to explain better, I would like to start off from the past, which is Hayabusa mission, and then transfer to our present effort, which is Hayabusa 2 mission. Just a couple of days ago, the flight model of sampling device came to ISS High Bay, and I attended to receive them, and then now it's installed in the flight model for the final integration test. So it's up and running. Okay, so first scientific premises. Well, I have to start off this view, this one, because as Adrian said, this is one of my collaboration with this institute. It's Leonid Meteor Storm Airborne Observation Campaign. During that time, I was doing my second postdoc at Johnson Space Center, but nevertheless, I was representative of Japanese delegation. And then this is, nowadays everyone has a high definition TV, but this was the very first usage of high definition TV with image intensifier for the scientific observation. So now it was only 13, 14 years ago, so we are amazingly coming that new technology catching up very quickly. So so starting off the cosmic dust, stratospheric particles, like a Scott, involved a lot, and Antarctic micrometeorite, meteor showers, and the zodiacal light. This is an image taken from the top of Mauna Kea in the area of the Subaru site. So my background is those cosmic dust research, And then, but there's only rare opportunity that you can study physics and chemistry of parent body from individual particles. And then Leonid meteor shower is one of the rare opportunities. But anything else, we could get tons of, literally tens of thousands of cosmic dust or meteorites on our hands. But the majority, if it's not all, are unknown of their origins. For the larger end, these more recent large events, Chelyabinsk events and DA-14 flyby. And then if you look at their parents' bodies, then you can see a whole range of different sizes for both cometary nuclei and asteroids. In Japanese language, we have some variation of what we call asteroids. We call extremely small asteroids and small asteroid, big asteroids. But in English, there's asteroids. So that's kind of difficulty I'm facing. These are all the list, the flyby images of the asteroids, and this is Lutetia flew by Rosetta. This is crossing 100 kilometers across. And it's Mathilde and these Ida. These are tens of kilometers across. And this red circle, inside of it is Itokawa. It's half kilometer. So, and then of course there are even larger ones, which is like 500 kilometers across, or the Vesta. So all those 3-4 order of magnitude differences, still we call asteroid. And then before Hayabusa era, I had a difficulty explaining why we think going to asteroids are important. It's a diversity of history of solar system, which can be revealed. However, all those Japanese scientists said, well, asteroid, right? And then, okay, so the US has flyby to like Ida or Mathilde. What else do you need? Or don't we go to the Vesta, or even Ceres, which is dwarf planet now? Why you have to go to Itokawa? But we never question ourselves. By knowing the planet Earth doesn't prove you don't have to go to Jupiter. In size-wise, it's only 1 order magnitude larger, right? So that the gaseous planets and the terrestrial planets are so different. And no one would say, well, we don't have to go to Jupiter because we know well the Earth. Similarly said, well, you don't have to go to half-kilometer asteroid Itokawa because we go to Vesta. We don't say that. But that's a psychological thing. So I'd very strongly propose you change the name terminology to next IU. Anyway, so those who are here today are, I think, well aware that the variety of different stage of solar system, we really have to study about primitive body to heavily differentiated bodies all the way. It's been like a snapshot of growth or the evolution of the planets. So, and then those are we so-called solar system small bodies. And what we like to study about small body exploration, I think in the end we like to pursue the origin and evolution of the solar system as not only ourselves, but also as a standard reference of planetary system in general nowadays. Just like the solar physicists study about the sun. Of course, we like to study about the sun for its sake, but also they study as astronomical subject because that's the closest stellar object we can study. So by studying sun, we like to extend the knowledge to celestial bodies in general. So we are now living in an era by studying planetary system, or our solar system, and also fossil of the early stage of the solar system in the forms of asteroids and comets, in order to better understand the planetary system elsewhere. And then one of the things, as like a Kepler mission now telling us that there are several thousands of extra solar planets out there, and then there should be more. There are super Earth and then other version of terrestrial bodies. But then next generation of the telescopic observations, like 30-meter diameter telescope, TMT, they try to do spectroscopic studies in a distance from the central stars. Because some of the images, we know that some of those stars are surrounded by planetary disks, and then those disks actually have a void, and then the void it's actually prove its existence of the planets within. So it is important to study structure and the material of within those planetary disks with respect to the distance from the central star. And the solar system is the best example to do that kind of study. So that's one of the driving force why we need to do sample return mission or meteoritic studies with known origins, where those parents' bodies come from. So for the closest end, which includes Earth and other terrestrial planets, S-type asteroids are sort of major ingredient, and then C-type asteroid is sort of overlaps. And then in the farther end, in Edgeworth Kuiper Belt region, the reachable fruits for us is a short period comet. So those are the targets exactly that what we do the sample return mission. And then in between these classes, in the closer end to the sun and the farther end away from the sun, is Jupiter Trojans. And then I will explain later why. So this is a sort of structure, so logarithmic structure of solar system to our knowledge. The largest end is hypothesized Oort cloud, and then in the inner region of that has Edgeworth Kuiper Belt. That's where Stardust samples might have come from. And then for the closest to the sun, it's Earth-crossing asteroid. That's the targets for the sample return mission, Hayabusa 1, 2, OSIRIS-REx, and the European proposal of Marco Polo R. And in between, just outside the main belt asteroid, or just outside of snow line, the Jupiter Trojan asteroid. That's a reservoir of approximately same order of numbers of asteroids in as main belt situated. They are flocking together in Lagrangian 4 and 5 points of the Jupiter orbit, and it has a relatively high inclination distribution comparing to main belt. For the thanks to successful recovery of Stardust sample from build 2, this is the cartoon of modified the X-wind model by Frank Hsu of Berkeley. And then this is sort of illustrates that within one single Stardust grain, it has a very high temperature mineral or components, such as CAI, are actually flocked together right next to amorphous silica, which is usually formed in a very cold area. So it has a very dynamic radial mixing in early stage of the solar system. This is a kind of thing rewriting our planetary formation theory by having the ground truth of astromaterial, and that's what we want to do. And Stardust is an excellent example. And probably we may be able to do something similar or even more surprising thing if we can bring sample back from Jupiter Trojans. Jupiter Trojans is one of, I wouldn't say the final, but one of the final frontiers of the solar system. Now that our space probe have visited, at least flew by every single planet by definition of IAU nowadays. And also in a few years' time, we will visit 2 dwarf planets, such as Ceres and Pluto. But we still have missing a very large population of our family of the solar system. That is Jupiter Trojan asteroids. And as heliocentric distance is concerned, in the comparison of the large asteroids, like 50 kilometers or larger, usually as farther away from the sun, D-type and T-type asteroid, which is relatively featureless, pitch black asteroid, start to dominate. Whereas closer end, we have a lot more S-type and also some igneous asteroid like Vesta type start to dominate. So, this is actually the unvisited reservoir of a large population of the solar system left. And going to the Jupiter Trojans is not just another asteroid mission. It's just more than that. This is a region we may change our concept of planetary system formation. In traditional view, Jupiter Trojan asteroid regarded as just leftover of building block of Jovian system. And then when Jupiter was formed at where it is now, that was a classic view. But if that was the case, then the Jupiter Trojan asteroid should be comparable to irregular satellites of Jupiter in prograde orbit. However, in 10-15 years in the past, people start to really think about how we can recreate the solar system in the same manner as other planetary system, which can have hot Jupiters or super Earth and all those bizarre planetary system. So in other words, planetary system is very, very diverse. That planetary formation theory, like Hayashi model and stuff like that, these has to be revisited and rethought about. And they start to generalize more into the formation. And then the theorists like Nice group in France, they start to claim that those giant planets, especially Jupiter and Saturn, were created much closer to the sun, and then then start to migrate outwards, and then once it migrate outwards, the orbital resonances between these 2 big planets would actually disrupt temporal orbit of all those leftovers in these regions, and they kicked out once. And once they arrive, so to present position, what we know as a Trojan object for both Jupiter and Neptune must come from outside. So these are called for migration theory, and then that's so that people think if that's the case, then present Neptune Trojan and Jupiter Trojan may be intruders from the Kuiper Belt regions. And then that migration period may coincide with so-called late heavy bombardment in a planetary region, including Earth. So those are kind of ongoing hypotheses. Then this planetary formation theory was sort of revitalized because of that. And then, so the present Jupiter Trojan has a fundamental key to prove or disprove this argument. If they are indeed intruders from outside, then we should compare the other object like Ceres from the Dawn spacecraft observation, or Pluto and Charon system, for that matter, from New Horizons, and also very first rendezvous to cometary nucleus, Churyumov-Gerasimenko, to be achieved by European Rosetta spacecraft in year or two from now. So next year, 2014-15 will be a very exciting year to all those first visit of 2 dwarf planets and the first rendezvous or even possible landing attempt to the cometary nuclei. And I think those knowledge will be directly benefit to the designing of Jupiter Trojan exploration. Second big question about Trojans is that although it is far enough from the sun that all those volatile materials can stay as ice or solid state, so-called it's beyond snow line, but apparently there's no clear water absorption band in spectroscopy. And then there are number of arguments, but there's no definitive proposals of the real answer. So therefore, we have to study up and close of the spectroscopy of the surface, or maybe inside of fresh crater, just like we saw Phoebe of the Saturnian satellite to see spectroscopic differences. And also, that is something to do with internal structure of this body, because like Frank Marchis and others studied about the binary of Trojans, and then people started knowing the bulk density of some of those are actually even less than 1 gram per cc. So that is to say, if they are completely composed of volatile with 100%, then that will give us around 1 or so. So we don't know why we have no water signature together with relatively low density. Or some of them has a high density. So we have to distinguish between material and structure by going there and do in-situ measurement. This is just an example of some of those spectral features of the Trojans. Trojans are those sort of pinkish background right there, together with main belt asteroids, a cometary nucleus, and Saturnian satellites. And recently, and the Rivkins, others have discovered water absorption in main belt C-type asteroid. And of course, they have lots of studies of heated experiment of carbonaceous meteorites on ground. But we didn't see these clear absorption band to over here or over there, and we don't know why. But this morning at AGU, they have some discussions about why this D-type Trojan looks so flat in the spectroscopy. It may be something to do with surface Legolas size rather than material, but we don't know the answer yet. And D-type asteroids have difficulty looking for terrestrial meteorite analog. In 10 years ago, well, even more than 10 years ago, Canadian Tagish Lake received this highly porous carbonaceous chondrites. Thereafter called it Tagish Lake meteorites. And some people may argue this will be a very good analog of D-type. But the other guy, the other group said it has too less the organics. And then, so that it has very inconclusive. And also the other camp started claiming that maybe ultra-carbonaceous micrometeorites discovered on Antarctica may be a good analog of D-type asteroid. So once again, there has no foundation of the clear answer, and the only sample return may be able to shed the light to this mystery. So for both structure of the solar planetary system and also material distribution of the solar system, Jupiter Trojan happened to sit in the middle. It was 5.2 AU, and of course in the vicinity of the heaviest planets of our solar system, and just beyond snow line. So everything fit there. And then 5.2 AU, it's not close, but the human already have sent robotic probes in the past. So we have some handle to do it. So next step is about technological challenges. Let me briefly explain what we did so far back in Japan. Unlike this country, we are still a latecomer of the solar system exploration. It was only 1985. It's just less than 30 years ago, Japan first sent a deep space probe. These are twin spacecraft, both flew by Comet Halley as part of International Halley Armada. It was just a very first experimental expedition. And then next deep space exploration, which means beyond orbit of the moon, was Hayabusa already. So the Hayabusa was defined as engineering demonstration or engineering verification spacecraft to demonstrate how you could possibly do deep space round trip and bring sample back to the Earth outside orbit of the moon. So launch was just 10 years ago, and then one Earth gravity assist with ion propulsion assist to increase extra delta V to reach to near-Earth asteroid called Itokawa, which is a Japanese name, and then stay there. Well, we originally planned to stay only 3 months, but ended up a year and a half. And then attempt the sampling by landing at least twice. And then bring the samples back to the Earth in 2010. The original plan was bring it back in 2007, but we are actually 3 years extra because of lots of malfunction and trouble we encountered. Just for the information, the cost of the total mission-wise was 180 million US dollars for that values 10 years ago. And that includes launcher, spacecraft, and operation. So when you say Discovery is your smallest, but now I think in present value is 500 million, or maybe originally they started 200. So I think Hayabusa is equivalent to the original Discovery cost cap. So in order to establish those deep space round trip, there are a number of new technology we have to verify. One of them is ion engine system for the as a main engine for the interplanetary cruise, and the other one is autonomous navigation and control by image processing. Because by the time we arrived Itokawa, which is 17 light minutes away from your operation mission control, so you really have to rely on the artificial intelligence embedded in Hayabusa at the time of touchdown. So, and surface sample collection from microgravity body. So the surface gravity is it's about 100,000th of g. So which means roughly 10 times less gravitational than inside of International Space Station. Well, you don't feel it anyway, but that's how the number goes. And direct Earth reentry from interplanetary space, unlike orbiting around the Earth, like a space shuttle. You directly go, just like artificial meteors. And you still have to make a capsule survived. So the examples for the comparison is a US program. The DS-1 was the first ion engine test. Deep Impact was beautifully impacted on the surface of the comet by autonomous navigation. And surface sampling collection will be achieved by OSIRIS-REx, probably within 10 years. And the direct Earth reentry from interplanetary space, Genesis and the Stardust already done that in this country. So, but in other words, the Hayabusa actually crammed those 4 or 5 missions into one, because we are so small in the space agency, and we are short in the budget, short in the manpower, so we can't afford to test every single of them by individual mission. So inevitably, this is an extremely high risk, high return project. And if you are PMP, the project management professional, this is the project number 1 you shouldn't do. I mean, yeah, Pinbox said, don't take that, it's too risky. But heck, we did it. So the orbit of the Hayabusa and Itokawa is like this. Green circle is orbit of Earth, center of the Sun, and blue is its orbit of Itokawa. Orbit, the closest point to the Sun of the Itokawa orbit is inside Earth, and the farthest point is outside Mars orbit. So it takes about a year and a half of the making round trip. So, and red circles or lines are the trajectory of Hayabusa in outbound and inbound. This is the daily life once your spacecraft is launched. The ISS, my institution, is a part of JAXA now, but it's originated from university institution, University of Tokyo, and created and become independent space agency until 2003, when the 3 respective agencies merged into JAXA. But the tradition is that because it's so low in the budget and so small number of the people, we can't subcontract to operators. So this is me operating the spacecraft. I'm not an engineer, I'm a planetary scientist. But you have to do the on-the-job training to do mission control. So the ISS academia, we only have 150 academia in 300 people in the institution. 150 is the technicians and administration. Other 150s are professors, or which at the same time will do space agency personnel. And among 150, roughly 100 are astronautical engineers developing a spacecraft or developing rockets. And the last 50 are scientists. Within the scientists, I think the majority is astronomers, X-ray astronomy, infrared, radios, and all the rest are planetary scientists. But the planetary scientists are usually composed mainly by solar terrestrial physicists. So all the like a planetary scientist who work on the small bodies in ISS. That's it. So maybe just 1% of the entire population. But because of that, you have to be very responsible for your baby. So since I was in charge of developing a sampling device and then in charge of bringing sample back, so I myself have to learn how to operate the spacecraft and make sure that Hayabusa do the right job. So this lasted 7 years. Of course, I didn't sit every single day, but the supervisors, it's a weekly job, and once you are assigned that week, this job is your priority number 1, no matter what. But we have approximately 1 dozen of supervisors per mission. So then, so that means every 3 months or so, your turn comes in. and work for the 7 days, lasting 7 years. Okay, and then Hayabusa revealed a number of the physical parameters of Itokawa. Of course, the orbital parameters elements are already determined from the ground observation, but all like size on rotational period very accurately, or spin axis positions, mass and bulk density. These are all measured after rendezvous to Itokawa. This is the comparison of the field of view of different instruments. Amica is optical camera, and XRS stands for X-ray spectrometer, and NIOS is near infrared spectrometer, and LiDAR is laser altimeter. Optical camera and laser altimeters are used for the navigation tool, but nonetheless we take it as a scientific tool as well. So in other words, we only have 2 genuinely science instruments on board Hayabusa that are XRS and NIOS, and these are footprints and the field of view of that. So, all those raw data and are already available to the public, and you can write the paper out of it from that website. And then at the time of the touchdown to collect samples, we have to look for where that's safest, and then hopefully it's meaningful for the science. And it turned out there's only one place we could possibly land. That is those smooth area, which is over here, so-called Muses-C regio. Because all the rest, more than 70% of entire surface of Itokawa is covered by the boulders, comparable size or even larger than the spacecraft itself. If that block is extremely large, much larger than landing ellipse of the spacecraft, you don't have to worry about it. You just land it there, right, somewhere. Or if the border is extremely much smaller than your spacecraft, once again you'll be safe. What you have to avoid is a border of comparable size of the spacecraft. Then it cannot be everywhere. So we end up try to land it over here, which is about 60 meters across, out of 540 meter in long axis. This is a good picture. I like it most. It's a shadow of Hayabusa against the sun, and this little highly illuminating spot is not dead pixel. It is a reflection of target marker. It's artificial lighthouse. So, because you really have to need some landmark to target to land, or at least you have a coordinate system to where you have references. Try to achieve it. So we just jetson one of those like softball size. Softball. Well, in fact, it looks like a softball, and it actually stitches like a softball, but and size is like softball, but in fact it's a metallic. It's aluminum ball, and it has a highly reflective fabric, just like what you usually have it when you run in the night. You have highly reflective clothing. That's exactly what we used. And then I will blow up this section like that. That's one of the closest image we got for the Hayabusa images, and this H represents height from the surface of asteroid. We took the images, so it's starting from the 80 to 60, 63 meter, and then below that the cameras start to defocus, so we won't be able to take good images. And if I blow up this, and then scale bar is 1 meter. So that means that this image is much smaller than this room. right? So one of those boulders may be size of your head. So that place is where we like to land it. So originally we plan to have those three the guns or the projectile to fire a 5-gram metallic bullet to either fracture bedrock or uplift ejecta, and then collect those powdery samples into this 1 meter long horn, which is actually has a funnel shape, in a conical shape, concentrated all the way to so-called sample catcher inside. This is the only place which will return to the Earth. So anyway, we attempt touchdown twice, and then I didn't go for the detail. Please read, if you want to know, please watch the Japanese movies, because they made 3 out of it. 3 movies out of 1 mission. It's incredible. But what I'm trying to get at is that touchdown 1 and 2 sites, we already identify where it is. And especially for the touchdown 2 is where the first special issue of initial analysis of the samples based upon, right here. And this is, it happened to be the foot of steepest mountain of this asteroid, which is called Shirakai Mountain. And this is an enhanced pseudo color image of Itokawa. And then those reddish dark area is more space weathered area, whereas bright bluish one is a fresh area. So that we can see you have a mixture of fresh and weathered particles if we collect samples from touchdown 2. And also we had evidence of granular migrations or landslide landscape in images. And then if we do 3D geopotential modeling, and that the geopotential vector is perfectly matches with apparent movement of the grains in those smooth area. So then we discovered that indeed there's actually the shaking such a small asteroid. And then these are example of 3D images or at least computer tomography of individual particles of retrieved Itokawa's particles, and then it has something pretty blocky and sharp edges, whereas the other one is rounded and then sort of eroded particles, and then that would somehow tell you that some of them are young particles and some of them are rounded, eroded by migrations. And also, we solved so-called meteorite asteroid paradox of ordinary chondrites by discovering very thin nanophase ion particles coating very top of individual particles. It's a bit like a lunar regolith, but it's much, much smaller scale. And then if you subtract that effect, the Itokawa near-infrared spectra perfectly match with freshly cut ordinary chondrite powders. So this is sort of the way we actually started shaking the Itokawas. Depending upon the internal structures, efficiency of local or global seismic activity by impacts will change. But nevertheless, the smaller particles more abundant, and then it's effective to local shakes. And we actually briefly calculate that Itokawa at least locally shaking almost every day. So and then we need a capsule to return, and this is capsule. I think you're there, right, Scott? Of course, after that, are you? I can't see him. Okay, this is Mike and Trevor. You're somewhere. Scott was also kindly enough to witness, as an international witness, to see that we did the right thing. And then we fetched the capsule, was looks like brand new. And then immediately after that, we brought some capsule back to ISS, and then where we are able to extract much less amount than we originally planned, but nevertheless ample amount to distribute to the rest of the world of the samples. And then with those initial analysis, which is has a special issue of science, we come up with a storyline of the past of the parent body of Itokawa, and how the Itokawa is formed by the accumulation of catastrophic disruption, and then how the present Itokawa is eroded or gardened in the surface. So this is actually the power of sample return. Just like we write a new chapter of the early radial mixing of the early stage of solar system by Stardust, we now know indeed Lopopile asteroid exists, and then we know now how they evolve. Hayabusa 2, then basically we try to repeat what went okay and try to improve what went wrong, because this is number 2, and then going to different target, which, at this time carbonaceous asteroid sample return. And then because of the carbonaceous asteroid, the interest lies to the volatiles and organics a lot. So therefore, we would like to have freshly excavated surface if we can. That's new thing compared to original Hayabusa. This is the flight model for the initial integration test in about a year ago. Now we are in the final integration at the same place at ISS. And the target is 1999 JU3. It's about size, it's about twice as big as Itokawa, and aspect ratio is more rounded than C Ota shape. And spectral type is CG. For comparison, the Hayabusa 1 and 2, your left-hand side is 1 and right-hand side is number 2. We have different telecommunication tools and X-band and K-band now, and ion engines become slightly stronger, and we include other things such as this. This is interesting. Hayabusa 1, we had presumably 8 detachable components, including 3 bullets. But for the Hayabusa 2, that would increase it to 15. We have 5 target markers, 3 sampler projectiles, which is not changed, 1 capsule, 3 Minerva, which is micro hopper rover, and small carry-on impactor, which is a new device to create artificial crater on the surface. And the mascot is German lander. And DCAM-3, which is not going to land on the surface, but it's actually a detachable your camera, just like your cell phone, to keep taking the pictures as the impactor will hit the surface. Ion engine will become stronger. It used to have the 5 to 6.5 to up to 8 millinewton, but now each ion engine becomes up to 10 millinewton, so that, and then we are able to lit 3 engines at the same time, so therefore we can go to 3 millinewton altogether. And lifetime has been proved by Hayabusa 1, more than 18,000 hours in collectively. So the engineering science payload as this. So the imaging camera and is the same, but near infrared are extended to much longer wavelengths, 3.2, so that we are looking for the hydration features and organic features. And thermal infrared imagers replaces the XRS, because now that we are more talking about Europe effects and all that. And then LiDAR is still there, and sampler is still there, and then small carry-on impactor, as I said, will be new addition. and DCAM, rover, and mascot. The small carrion impactor is a completely new challenge to excavate artificially the carbonaceous asteroid and try to disclose underground subsurface material on the surface. Basically, what it does is this. This is a copper shell. So we are not exploding the explosives on the surface of asteroid. So let me clear that. We are actually hitting by the metal, just like a deep impact, and then in hypervelocity speed, 2 kilometers per second. So, and then this is deformed things. So you see the bow shock here. So after release, it's deformed and then hit the target and then make a crater. That should be executed after initial surface sampling is complete, of course. And then if the after the impact occurs, and then we are able to identify the new crater, and then we judge it's safe to land, then we'll try to do additional sampling attempt, hoping to grab some freshly ejected material. So the surface sampling and subsurface sampling, these are the combination of the Hayabusa 2, and that's a new addition from Hayabusa 1. Hey, Mike. Wow. For the Hayabusa 1, we could have had American rover from JPL Supply, but they canceled it. So that people who know well about Hayabusa's got a big square hole in one panel, which is over here, structurally. So of course we cover up the MLI. But for the Hayabusa 2, we use that area to accommodate a German robot. So it's called Mobile Asteroid Surface Scout Mascot, which is about 10 kilograms, including releasing mechanism. And then with that 3 kilograms, they actually carries magnetometers and radiometer and wide-angle camera and near-infrared microspectrometer, so-called microomega. These are all supplied by the European colleagues. And then this is the new addition for the comparing to the Hayabusa 1. So this is a Hayabusa family. So starting off the Hayabusa, and then we try to do the tradition or building up the expertise even more. And our American friends and European friends try to do similar things, which is most welcoming. But we like to go farther away because we now have S-type, C-type, and now try to go to D-type. That's the Jupiter Trojans coming into play. Of course, Hayabusa cannot go to 5.2 AU because the solar cell is small. The solar puddle is so small. But deploying extremely large array, such as 3,000 square meters, then what you can do is this. If you deploy 3,000 square meter ultra-thin solar array at 5.2 AU, you can produce 10 kilowatt. And you can carry the payload mass of 500 kilograms. That is to say, comparing to Juno, which is on the way to Jupiter, now it carries less than 500 watt production of rigid array, and then carries less than 100 kilograms of payload. So this is potentially the game-changing technology without asking ASRG or MMRTG for that matter. Of course, it takes long. We studied almost 10 years of history of solar cell test starting from high-altitude balloon to sounding rocket to piggyback in low Earth orbit and piggyback to interplanetary, which is IKAROS. And then we are finally ready. Interplanetary piggyback demonstration is called IKAROS. It was launched in 2010 as a piggyback of the Venus orbiter and two-stage deployment. And by the way, this is the Venus here. And then we used a detachable camera to take pictures of mothership. So as it go away from the mothership, every second your cell phone-like camera took pictures and sent it back to the mothership. And then certainly, yeah, the array. This is a 200 square meter solar cells, which is 15 times less or smaller than what we are trying to do. But I think it did a good job for the world's first solar array deployment. And then as soon as full deployment occurs, this x-axis is the time and y-axis is the velocity. Therefore, this slope tells you the acceleration. So as soon as the solar array deploys, the acceleration occurs. This is a proof that we had the solar photon accelerations in 1.12 millinewton, although it's small. So by using this technology, the notional mission milestone of solar power cell is this. We are now in a stage of working group and then try to come up with a project proposal, hopefully within 2 years. And if we select it, and then earliest launch will be early 2020s, and then make a rendezvous to Trojans in 2030. And then, yes, we still investigating option of sample return from Trojans, and then it's going to be a 20 years mission. Or so it's coming back in 2036, nevertheless. And ideal target, we are working on 24 of targets nowadays for both L5 and L4, but this is ideal situation. It's going to be it'll be a large enough as a survivor from the genesis of the solar system, and the red slope Trojans, and with a satellite existing so that we have confidence of internal structures and bulk densities. Of course, it's very difficult to find binaries, and Frank knows the best in the world about that difficulty. But that if we can choose this type of the target, that'd be wonderful. And notional instruments are the imager spectroscopy, LIDAR, and thermal, and radio science and dust analyzer, and possibly lander. And those yellow hatches are also the science. It can be achieved by return sample analysis. So I think I have to wrap it up. So the deep space round trip, Jupiter Trojans, and even farther. Okay, what I'm going to talk about is future, super future. It's no official responsibility of the JAXA from now on. This is only my personal preferences. But to study that, this is a reality. In top half is existing the space missions, either operation or preparation. And lower half is a roadmap or proposal or studies which has been done, either Europe, United States, or Japan. Now what you can see is that in early 2020s, US, Europe, and Japan all are going to, or all are having study about the going to Trojans. Of course, NASA decadal new frontier candidates, one of them is the Trojans, and then ESA cosmic vision candidates are also a Trojan multiple flyby. And Japan is only one to go, not only go to Trojans, but make a rendezvous and then try hopefully coming back. This is sort of cartoon of our vision that what may end up for the, well, at least concept of the deep space round trip exploration, especially in terms of astrobiology view, because I thought this is appropriate to the City Institute. So the life precursor and chemical evolution of panspermia or inhabited life search or habitability search, there are a variety of astrobiology themes, but and then you have to pick right target, and then whether you go one-way in-situ measurement or round-trip sample return. But if we become able to bring sample back from outer planetary region, such as Trojans, or even farther away, e.g. Enceladus, then I think we'll have a whole new science out there. This is cartoon of the concept of basically the, I'm not the first to invent this idea, but the number of people say, well, bring the Stardust spacecraft to geyser of Enceladus and bring it back to the Earth. Because you got relatively low, like 2 kilometer to 4 kilometer per second encounter velocity to ice plumes. And then, of course, we have to deal with the planetary protections, but we have some idea how to deal with it. And then these things are already started. Next year, hopefully, that we'll launch our own two-stage aerogel to be on board in International Space Station for called Tampopo project. Tampopo stands for dandelion. This is an exposed facility of Kibo, the Japanese module. This is the only place on ISS to do exposed experiment without asking astronauts to do EVA. So that means cheap, right? So you have an airlock to either put it out or put it in your apparatus, and you have a robot arm to have it exposed things or bring it back to interior. And we have now two-stage aerogel to exposed. And hopefully we'll start from year 2, and then we'll continue to 3 consecutive years. Every year we bring the samples back, so up to 3 years, and then see the accumulation of the effect. I think this is my last chart, and I would like to take a question as much as I can. This is the chart of pioneers of deep space explorations. And then Trojans are actually final remaining frontier today. The way you look at is that the y-axis is the different type of missions. The top one is easy, and the bottom one is most difficult. Starting off from flyby, orbiter, lander rover, sample return, and human mission. And then x-axis are your destinations from sort of heliocentric order, Moon to all the way to Pluto. And the yellow hatch are the frontier of that particular destination as of today. And the U stands for United States, R stands for Russia, E, Europe, J, Japan, and there's some China and India as well on the Moon. But anyway, the way you look at it is that all those frontiers, majorities are achieved by the United States. I really appreciate that. Well, thank you. But we so far have some handle of about asteroids. And of course, US is catching up. Well, the OSIRIS-REx is coming up, and even your president wants to send a human to the asteroid. So that's there. So it's catching up. But I think our next target is really outer planets, and to bring samples back from outer planet. And not only for the technological challenges, but also the very scientific reason I explained in the first third of this talk. And then once we have that grip of the technology, we may be able to challenge ourselves to go to even farther, such as Enceladus. I stop here and take questions. Thank you very much.
Hajime, if I can start with the first question. Yeah. You mentioned that on Hayabusa there were some pellets or projectiles that were going to be fired into Itokawa. What happened to those projectiles?
They were not fired. for the Hayabusa 1. Okay, I watched the movie.
That was my other question. Are the movies in English?
I think it's English subtitles.
Subtitles, right?
Subtitles,
okay,
DVD available. But of course, I will tell you the reason. We did have 2 touchdowns in November 2005. And the first touchdown meant to be aborted. So in other words, Hayabusa was descending to the surface of the Itokawa, but the spacecraft detected some obstacle just underneath. So if the spacecraft kept going, then the solar array may get damaged. So then there's algorithm. If those obstacle sensor detected something, you stop descending and go to emergency ascent. However, there's one more additional command that says, if you are tilt too much, and then if you go to emergency ascent, you also may have a chance to hit something, be back. So therefore, if you tilt too much, don't stop, just keep going. So there's 2 contradicting command taken hand. So therefore, Hayabusa stopped descending, for the engine-wise, but just keep falling for the free fall by the gravitational pull of the Itokawa, and then just bounce a couple of times. Okay. And then stay at the touchdown 1 point about half an hour. And of course, at that time, I was supervisor to emergency ascent. So that means the first one, Hayabusa did not fire accordingly, collectively, due to abort command. And for the second one, which will be our last attempt, we almost killed most of abort command, almost go for broke, which will never come back until you get the sample. And then we just gave it, and Hayabusa did it. It was we almost tried 5 or 6 times of including rehearsal and the actual attempt of sampling, which is, it's very, very difficult to land irregularly shaped microgravity body. That's extremely difficult. But it was the second attempt was perfect touchdown. Perfect touchdown as we originally planned. And Hayabusa touched only tip of the horn, stay only a few seconds, and then the command to fire the bullet was issued, and then it ascended safely. So looks perfect, except there's another contradicting command occurred. The Hayabusa 1 had sort of 2 brains. One is a GNC guidance navigation control brain. The other one is a pyrotechnic control brain. And then apparently the GNC allows a trigger to issue the bullet after confirmation of the physical contact of tip of the horn. And then we are able to track down the program. However, just before that, the pyrotechnic control command issued to the safeguard the projectile. So therefore, that firing a triggering command was cancelled because of those safeguard commands. So to the lesson to be learned is that mainly 2. If you go to uncharted asteroid, make sure you have enough time, right? Because Hayabusa arrived at September, and then did first attempt of sampling November, only 2 months. And then so for Hayabusa 2 case, we stay 18 months. So and then in between first and second attempt, we should have enough time to do all possible program checks. And second lesson is that you should have only one brain, right? So the Hayabusa 2 now has integrated CPU to control everything in one brain.
You mentioned bringing back samples of the ice plume from Enceladus.
Yes.
So could you just talk a little bit about how the samples are protected? For example, if you brought it back to Earth, it wouldn't be ice for very long. Do you cool samples? Do you use inert noble gases in order to like protect them? Could you just speak briefly on that?
Sure. Yeah. Of course, the Enceladus icy plume sample return is just a still idea, but of course, the issue you address is very important. Hyperburst impacts of volatiles. Of course, it's usually evaporates and then recondensates. So the one idea is to have a cold trap. So intentionally vaporize it and trap it. That's one. And also icy plume also have some residues of the particles from seafloor, because we know there's the seafloor minerals, because the Cassini dust analyzer told us there's sodium, potassium, as well as organics and also silicates. So if they have like nanosilicates and others, it has a very good constraint of what the thermal vent activity was like on the bottom of seafloor of Enceladus. For those ones, we would like to capture intact at the same fashion as Stardust. However, we would like to keep it sealing, containing seal. For the Stardust, the capsule believe as enters atmosphere of the Earth, but we would like to have the vacuum sealing. Of course, that vacuum sealing also necessary for the matter of planetary protection protocol as of today.
Any more questions? I have one question about, could you tell me what's the difference between Minerva and Mascot?
There are, yeah.
Could you tell us a little bit more about the differences between instrument and mobility?
Okay, yeah. So the Mascot, I had the cartoon. Mascot is 10 kilogram big for us, the big suitcase size robot. It doesn't have any wheels or arms or head, but it's a robot. And it carries 3 kilogram of scientific instruments. Whereas Minerva is only 1 kilogram or a little bit heavier. So it's about a tenth of the weight of Mascot. And then it's basically it's an engineering demonstration. However, it also carries small cameras and thermometers and maybe dust counters and those smallest scientific instruments. So that to show Mascot is provided by DLR for the surface scientific investigation, whereas Minerva provided by the JAXA for the technology advancement of hopping and also at this time inching the surface of microgravity bodies. So that's the major purposes of those two. But nevertheless, the Minerva 2 also have some scientific measurements.
Yeah.
Derek.
Thank you for that talk. It's a very nice talk. I got a couple of points. One is, you talked about protecting the sample on a sample return from Enceladus. Did you mention how the samples from Hayabusa 2 are going to be preserved? You have a cryogenic container, or?
No, I didn't mention that. Hayabusa 2 target is C-type asteroid at NEO. So in NEO surface, that it's already become super hot anyway. So that there's no need for the cryogenic things. Maybe for the subsurface, for that matter, but nevertheless, we don't go for the cryogenic preservation. However, because of C-type asteroid, we have scientific requirements to collect the degassed volatiles and noble gases, as well as the preservation of organics. Therefore, we change the sealing mechanism from double ring Biton, double O-ring Biton as Hayabusa 1 to metallic sealing for the Hayabusa 2. So that way, hopefully we can actually vacuum seal in tight and though there's no gas leakage, at least immediately after the landing. And also, suppose this is capsule sample container. For the Hayabusa 2, Hayabusa 1, we have to rigorously physically open it, the lid. And then the procedure was quite violent. And that may be the cause that some leakage or the intrusion of the air came up. So the Hayabusa 2, we added new things. It's on the bottom of collector, container, we had a very thin metallic wall. You can actually punctuate your needles and suck any remaining gas inside even before opening the capsule.
When it gets back.
Yeah, so the most likely that operation should be done at the landing site, which is Rumela Desert.
Can I ask another one?
Yeah, 1, 2.
I'll be real quick.
Sure.
I'm curious about this projectile you're going to fire on Hayabusa 2. You said it was basically a plastic explosive and then a metal sheet of some sort. Is there any recoil for the spacecraft?
Indeed. That's a very good point, which I skipped. This is a cartoon. What happens is that this is where the explosion occurs, right? And then the metallic, metallic projectile is fired over here, and then this green shape is an impact ejector cone. Those red arrow indicates the fragments of the SCI system itself. It's sort of suiciding itself. So therefore, spacecraft, once it's released, the SCI, it goes immediately going to physical shelter of the shadow of asteroid itself. So that way you can actually avoid the fragment to getting hit you. Is
that a dangerous process?
It is very. Well, we think it's ample time to do the operation, but of course it's a risk-taking operation. Yeah. I think you have.
Okay.
One, yeah.
At the very beginning of the talk, you showed an accretion disk, and I didn't see the scale there. Like where was the Earth orbit and where is the Jupiter orbit on that accretion disk?
I mean, over here?
Yeah, before that, there was it showed an accretion disk and material coming in to form the sun, or maybe it's just after this.
No, probably this is the one you're talking about.
Yeah, okay, no,
quite?
it was not that.
Okay.
But it showed material coming in to
Oh, you
form
mean
the
this
solar
one?
system. That
Okay,
one, yeah.
right.
What's the Earth orbit and Jupiter orbit on that?
Okay, I think this is the logarithmic
I see one
scale. Yeah, AU. So
1 AU.
So yeah,
and
this
5
one.
AU.
This is Earth.
Okay, and then Jupiter's
Jupiter
in
is somewhere down
between 1
there.
and 10. Yeah.
Yeah. Okay.
Okay, towards 10. Yeah.
Okay. Hajime, we have a special SETI Talks mug for you. It's probably big enough to contain some sample back from Hayabusa 2. I probably wouldn't recommend.
Well, I have to sterilize this first, right?
Right, exactly. I wouldn't recommend doing coffee with samples as well. But yeah, please join me in thanking Hajime for his great talk.
Thank you.
If you have any final questions that you want to address to him, feel free to come up now.
Thank you. Thanks. こんにちは。藤島さん。